Hello, hello students. Our topic today is realization of monolithic IC technology. Okay, so this is the basic structure of a monolithic IC, which have four layers of different materials. So we gonna uh, put together all these materials to form a monolithic IC. Before seeing what is actual planar process in preparing this monolithic IC technology, let us see what is monolithic. A monolithic circuit means a circuit fabricated from a single stone or a single crystal. The word monolithic is derived from the Greek meaning single, and litho means stone. The monolithic ICs are in fact made in a single piece of single crystal silicon. The fabrication of discrete devices such as transistor, diode, and IC in general can be done by the same technology. The various manufacturing processes by which IC is fabricated usually takes place through a single plane, and the technology is also referred to as planar technology. So, monolithic IC manufacturing process being the base layer of the IC. Generally, first a simple circuit when fabricated by single silicon planar technology will have the cross-sectional view as shown in figure. The basic structure of an integrated circuit consists of four distinct layers. First layer is p-type silicon substrate upon which the integrated circuit is to be built. The second layer is thin n-type material which is grown as a single crystal extension of the substrate. Third layer is silicon dioxide and the fourth layer is aluminium. So being the base layer of the IC, the p-type is silicon is first built in the IC. A single crystal of silicon of p-type is grown in dimension of 250 mm length and 25 mm diameter. The silicon is then cut into thin slices with high precision using a diamond saw. Each wafer will precisely have a thickness of 200 micrometer and a diameter of 25 micrometer. These thin slices are termed as wafers. These wafers may be circular or rectangular in shape with respect to the shape of the IC. After cutting hundreds of them, each wafer is polished and cleaned to form a p-type substrate layer. Next one is the n-type epitaxial growth. The n-type epitaxial film is grown on the p-type substrate. This ultimately becomes the collective region of the transistor or an element of the diode and a diffused capacitor associated with the circuit. So in general, it can be said that all active and passive components are fabricated within this layer. The resistivity of an epitaxial layer is of the order of 0.1 to 0.5 ohm centimeter. This is done by placing the n-type layer on top of the p-type and heating them inside a diffusion furnace at a very high temperature. After heating, a gas mixture, silicon atoms and pentavalent atoms are also passed over the layer. This forms the epitaxial layer on the substrate. All the components required for the circuit are built on top of this layer. This layer is then cooled down, polished and cleaned. Now the silicon dioxide insulation layer. This layer requires contamination of the n layer epitaxy. This layer is only 1 micrometer thin and is grown by exposing the epitaxial layer to oxygen atmosphere at 10,000 Celsius. A detailed image showing the p-type, n-type, epitaxial layer and SiO2 layer is given in image. Next one is the photolithographic for SiO2. So, in this process, the SiO2 layer is coated with a thin layer of a photosensitive material called photoresist. A large black and white pattern is made in the desired pattern, where the black pattern represents the area of opening and the white pattern represents the area that is left dry. Next one is the isolation diffusion. The temperature and the time period of isolation diffusion should be carefully monitored and controlled. As a result of the isolation diffusion, the formation of n-type region called isolation island occurs. So the isolation diffusion, four components have to be fabricated. So we require four islands which are isolated. For this, SiO2 is removed from 5 different places using photolithographic technique. The wafer is next subjected to a heavy p-type diffusion for a long time interval so that p-type impurities penetrate the n-type epitaxial layer and reach the p-type substrate. The area under the SiO2 or n-type islands that are completely surrounded by p-type modes. As long as the p-n junction between the two isolation islands are held at reverse bias, the p-type substrate is held at a negative potential with respect to the n-type isolation islands. These regions are electrically isolated from each other by two back-to-back diodes providing the desired solution. Next one is the base diffusion. In base diffusion, a new layer of SiO2 is grown over the entire wafer and a new pattern of openings is formed using the photolithographic technique. Now, a p-type impurities such as boron are diffused through the openings into the islands of n-type epitaxial silicon. The depth of this diffusion must be controlled so that it does not penetrate through the n layer into the substrate. This diffusion is utilized to form base region of the transistor, resistor, the anode of the diode and the junction capacitor. Next one is the emitter diffusion. A new layer of SiO2 is again grown over the entire wafer surface and selectively etched to form a new set of windows. An n-type impurity such as phosphor is diffused through them. This forms transmitter, emitter and cathode region of diode. Windows are also etched into n region where the contacts is to be made with the n-type layer. Heavy concentration of phosphorus is diffused into this region simultaneously with the emitter diffusion. The reasons for using heavily doped n regions can be explained. Aluminium, normally used for making interconnections, is a p-type impurity in silicon and can produce an unwanted rectifying contact with the lightly doped n material. However, heavy concentration of phosphorus doping causes a high degree of damage to the Si lattice, thus effectively making it semi-metallic. This N plus layer thus makes a good ohmic contact with the aluminium layer. Next one is the aluminium metallization. So the IC chip is now complete with all the active and passive devices, and only interconnections between the various components have to be made in accordance with the circuit. The chip is further subjected to the process of formation of a new SiO2 layer and masked etching to open a new set of windows at the point where the contacts have to be made. Thus, it has and the final stage of the IC manufacturing is the scribbing and mounting. After the metallization process, the silicon wafer is then scribed with a diamond dip tool and separated into individual chips. Each chip is then mounted on a ceramic wafer and is attached to a suitable header. Next, the package leads are connected to the IC chip by bonding of aluminum or gold wire. from the terminal pad. Thank you.